Well, we have this series of questions about a block on an incline, and we demonstrated that. Here's the incline, here's the block. We go up, we go up, we go up, we go up. At some point, if we keep going up, block begins accelerating down the ramp. We say that that acceleration is the a sub zero here. And then there are some questions about it. Okay, now I say the block is 2 feet long. I gave you examples of different heights, but I really want you to work this out with symbols. Just let L be the length of the incline. Let H be the height of this end with respect to this end. Answer some questions about the force of friction. Depending on H. One thing that I don't see on anybody's paper, although I see something pretty close on at least one, is I don't see the x-axis. I don't see a y-axis. And I don't see my blue chalk. Okay, I don't see the weight vector labeled. I don't see the weight vector projected on the x and y axes. Now, there might be some symbols down there that are related to this, but if you haven't, in the first 10 seconds after looking at this thing, drawn this picture, think about why not and think about why you should. I've done the picture several times in class. You've seen it in your book. And it's relevant to a couple of the problems that you submitted. Okay. You have a couple of things about inclines there. Anytime you have an incline, a mass on an incline, you draw this picture. Okay, then you draw a normal force. Perpendicular to the incline. That much is automatic. Then, just to keep you moving a little bit, you need to know this angle here in order to calculate these components. So another thing, I'm not sure your book does it, but I think maybe they do. But the standard book I've always used for this course that nobody can afford anymore is the old Sears and Zamansky text, but Young and Freeman. I think it's Freeman and somebody else now. It's a great text. But the one we're using, the OpenStack text, is pretty good. I'm not sure they do this, but we can't do anything with that vector. So we replace it with these two vectors. The weight vector is totally equivalent to having a force here and a force here. Okay. If I exert these two forces on this mass, it's going to move, behave exactly as it would if I exerted this force. But it can't do both. So that's why I kind of put a little wavy line through this to show, yeah, that's the force, but here are the components we're going to use. And of course, you learned a couple of chapters ago, whenever you're trying to do anything with vectors, you want to do it in perpendicular components. So kind of take a lesson on that. The other thing, I haven't given you an angle. A lot of times you're given an angle, but I've given you everything you need to know the angle. And you don't even really need to know the angle. All you need to know is the sine and cosine of that angle. Okay, so we're going to say theta is the angle in here. Tangent of theta equals, oh, sorry, you don't know the tangent. That's a sine there. I can't read that. Not everybody even knows how to read script, so. Sine of theta equals h over L. Cosine of theta is the square root of 1 minus the sine squared of theta. The tangent of theta is the sine over cosine. And it's going to be h over L times this, but you multiply the L through here and get a slightly simpler thing, and you should be able to do that algebra simple. I mean, it should be simple for people who've been through your calculus, semester linear algebra, okay? If it isn't, keep working on your algebra. You're not going to need the tangent to answer these questions, but if you do need it, there it is. And you can also say that, okay, if this is h and this is L, this is the square root of L squared minus h squared. So this is h over, the tangent is h over the square root of L squared minus h squared, which is actually simpler than dividing this by this, but it comes out the same. So take my words for what they're worth, but there's what you got to start with. I just realized it should have the frictional force because now you have 1, 2, 3, 4 forces that you can express in terms of the symbols I gave you and use these forces to answer the question. There's a subtlety in answering this question. There's something you got to know about friction. I told you about it last time, and your book has told you about it. So let's see what you can do with it. Okay, just addressing some of the things I see here. I'm still not seeing projection lines and correct vectors here on every paper. I'm seeing on some papers. Sometimes I'm seeing one of the projection lines and one of these and so forth. Now, one flaw in my picture here, my projection line here doesn't quite go at a right angle with the y-axis. So it makes this vector look a little shorter than it really should be. Okay, well, that's okay, as long as your vector doesn't just end like here, it's plausible. But we want to see that projection line. If the projection line doesn't make a 90-degree angle, maybe it only makes an 80-degree angle. I'm not going to say much about it right now. I just want to make sure it's as close to 90 degrees as you can eyeball. And sometimes it's hard to draw that when you're first drawing these pictures. Okay. I don't see angles being labeled. There's theta. And here's theta. How do I know this is theta? Well, intuitively, if this thing starts flat, then mg, well, then your y-axis is straight up and your x-axis is straight across, and your mg is right along the y-axis, and your x-axis is horizontal, and your normal force is straight up. If you start tilting the thing a little bit, your y-axis tilts out, but mg stays where it is. That makes sense? If I was to tilt this a little more, make the angle a little bigger, well, the y-axis would have to go this way. The whole x and y coordinate system would rotate this way, and that would rotate the y-axis away from this vector. If I rotate it back to where the y-axis is vertical, this angle shrinks to 0, and so does this, right? Then as I rotate it away from that, this angle and this angle stay the same. Now, there's a geometric argument. You should know that geometric argument, that the x-axis makes angle theta with horizontal. So the y-axis is going to make angle theta with vertical, because the x and y axes are perpendicular. So just simple seventh grade geometric argument. If they ever taught you geometric arguments in seventh grade, like they no longer do, or even high school. Okay. So makes it a little difficult to really understand deeply what's going on here. So, but you can do it. It's really a middle school argument, and y'all are way beyond middle school arguments. So you can do it. Just make sure you do. Okay. Make sure you understand why these angles are equal. Now, once you know this, then you have a triangle here, here, and here. You know, this point to this point to this point, and this angle is also theta, so you probably ought to label it theta, so that you know that mg is your hypotenuse, and this thing is then the hypotenuse. Well, this is then the opposite side, so it's hypotenuse times the opposite side, right? Yeah, it said hypotenuse times the opposite side, which makes no sense. The opposite side is the hypotenuse times the sine of the angle. That this sine of the angle is opposite over hypotenuse, okay? And similarly, here's the same or similar triangle, and this side is the hypotenuse times the cosine. Make sure you are never thrown by that ever again. Okay? That's just totally basic trigonometry, but of course it's applied to this picture, which has a few complications. But you got to run into this picture again and again. And understanding this picture, not just memorizing that this is theta and this is theta and this is theta, and that's a sine and that's a cosine, but seeing the sine and the cosine, seeing opposite over hypotenuse, seeing adjacent over hypotenuse, okay? You really need to see that. Otherwise, you're going to get misled and make mistakes, and you're not going to understand very deeply what it is you're doing. Now, you got to keep doing problems. You're going to get better and better at it, but make sure you have the foundation and understand how at least to look at this picture so you know how to look at other pictures. Well, with that, can you label the length of this vector and length of this vector and the length of this vector and tell me something about this one? It's all there in the picture. So I'm going to tell you because we need to move on, but okay, this is, I'm going to call it mgx equals mg sine theta. And if you have no forces, never mind. There's a case, if you have a force, I'm not going to say it now. Sorry. Okay. It's quite the right time to say it. So there's your mgx. Okay, I'm going to say mgy component is negative mg cosine theta. It's clear that it's in the negative y direction. And then your normal force is not equal to mgy, because mgy is in the negative y direction. It's equal to plus mg cosine theta. Why? Because you have no other forces in the vertical direction. Okay. So I could say, and since I've got arrows over these things, I'm just going to be ambiguous for now. Fn plus negative mg cosine theta equals 0. Because of y equilibrium in the y direction. There are only two forces right now in the y direction. That implies this, which implies this. This is why the normal force is mg cosine theta. Now, people get in the habit of then saying that the net force in the x direction is mg sine theta. Well, it isn't. In this case, it isn't because you got friction there. And saying that the normal force is mg cosine theta. You can't say that unless you know that there are no other forces with vertical components. If there's a push in the horizontal direction, that push has a horizontal and a vertical component. So you no longer can say that these forces add up to 0. You got to take that other vertical component in there and include it in what's equal to 0. So if I'm pushing this way, my vertical component of this force, or my y component of this force, is pushing upwards, so it means there's less normal force. If I'm pushing this way, back to the left horizontally, then my push has a horizontal component, or an x component, which tends to push the block up the ramp, and a y component, which tends to push the block into the ramp. If you ever compare what it feels like to push a heavy wheelbarrow over heavy, uneven ground as opposed to pull it, which is easier, push or pull? Pull. Who was that out in the hall? Okay. Every once in a while somebody walks by here and answers my question. Once asked about the meaning of the universe, and somebody's walked by the hall, they started telling me, and they just started mumbling. I couldn't understand what they said, so I had to figure it out for myself. It's ridiculous. Anyhow, okay. So what was I saying? Simply, you've got to write your equilibrium conditions carefully. And your book shows you how you might structure those. I'd go with the structure of some of the example problems I see. Okay. And I semi-structure things, but I'm doing explanations and so forth, and adding things in response to what I see you all doing. And I'm not that great an organizer anyway. Okay, if I was solving the problem for myself, I'd organize a little better. So here are the things that go into solving this problem. Now, what we're really after is the frictional force. So given that I've got all three of these forces labeled, what can you tell me about the frictional force? Okay, well, quickly, go on the picture again. It should be obvious that the picture is going to look like this with mg acting down here, an x-axis in this direction, and a y-axis in this direction. Now, why is that? It's so that the x-axis is the motion of any possible direction, the direction of any possible motion, and the y-axis is a direction in which there's no motion. So you have equilibrium in the y direction, and maybe you have equilibrium in the x direction, and maybe you don't. Now, you know you have one force, gravity is acting downward. You can project right angles. I should put my theta here, then it's hard to read, but anyhow, you project at right angles, and you get the components of mg. So you can cross out mg, total equivalent to components. This component, well, where's your angle theta? To get these components, you have to know the angle of mg with one axis or another. Well, the angle is theta here. And of course, you have theta here because this projection line is parallel to the y-axis. Okay. So these angles are opposite sides of transversal, and they're equal. So anyhow, you have the angle theta here, the angle theta here, and just using your basic trigonometry, you find that this force is mg sine theta, and this force is negative mg cosine theta. Then, if you have no other forces in the vertical direction, you have equilibrium in the y direction. So you're going to have a normal force to equilibrate that. Now, if you got another force in the y direction, then you got to do what we did up here. You got to add up all the forces in the y direction, set them equal to 0. And this vector should be as long as this one. I didn't make it long enough. So let's just go ahead and make it long enough and then extend the y-axis a little further. A little sloppy, but there it is. Then you might also have a frictional force. It's going to be such that it resists motion. Meaning, if the frictional force was in this direction, there would be motion in that direction. Okay? If there's motion in this direction due to this force, then friction is trying to retard it. So friction is always going to be opposite to whatever direction the thing is moving in, or to put it intuitively, try to move in. Okay, as determined by the rest of the forces that are acting on the system or on the mass. Okay, so now we can do this. We can say X, Y. We have mg sine theta, and yeah, I'll put a negative. I really kind of don't like to do that, but I do. What I like to do is put all angles on a 360-degree basis with the positive x-axis and go from there. But so then you don't have to worry about whether that's negative or that's positive. Okay, there it is. In the y direction, we have negative mg cosine theta, and f normal. There's a list of our forces. There's a picture of our forces, and the list is pretty consistent with our picture. we can list the sum of our X forces. That's mg sine theta minus the force of friction. Our Y forces, write the F before you write the M. Okay, I'm just going to do them in the order I wrote them. mg cosine theta plus your normal force. Equilibrium, sum of the X forces equals sum of the Y forces equals 0. So now I'm going to skip this step. I'm going to say, if you let this equal to 0, you find that the force of friction has magnitude mg sine theta. I didn't draw it that way, did I? But in the case of the block on this incline, when I'm at that angle, which is about like so, that block is stationary, which means that the appropriate picture for the block on the incline then your picture, excuse me for blocking the board here, we'll get it in a minute. Not going to be much of a surprise. Without labeling anything, your picture is going to look like this. It's very rough, but this and this will be equal and opposite, indicating that the block is stationary. If you're on a much steeper block, well, also normal force equals mg cosine theta. What you can't say is that force of friction is mu static times mg. Okay, mu static times mg might be much bigger than this, and it is. In other words, this block is here, thing is stationary. Okay, if I move it up to here, the x and y axes rotate, this component becomes bigger, and this vector has to equilibrate it and becomes bigger. In other words, we have more force acting in the direction of the incline here than we do here. The frictional force can't be bigger than the force of the component of the weight down the incline. And the component of the weight down the incline is bigger here than it is here. So the frictional force is bigger here than it is here. That makes sense? The frictional force is not equal to the coefficient of friction times the normal force until we get about here. It starts to move a little bit. Okay. So I'll make a note. It's this frictional force is less than or equal to times, so less than or equal to the static friction times the normal force. Until that very on that refrigerator, you push harder, friction's not exerting a force that's greater than your push. But US times Fn, coefficient of friction times the weight of your refrigerator, is greater than your force until you exert enough force to start it moving. You'll have to throw a hip into it so you don't tip it over. Okay? Either that or push really low. Well, okay. Now I'll leave you to reason out the rest of it. Picture I have here would correspond to pretty low coefficient of friction. Maybe this is a very smooth surface. Okay, maybe there's a little ice on it or something. Okay, and then this picture would correspond because the friction is less. This corresponds not to an equilibrium position. This corresponds to a position in which you have an acceleration down the incline. Okay, let's draw that quickly. Without labeling these things or calling a mass in here or anything. Acceleration is not equal to zero. I draw it like this. Assuming these vectors are equal and opposite, and these are, this is equilibrium. And if I draw it like this, acceleration is not equal to zero, but this thing here ain't friction because it's bigger than the normal force. Okay? At least not friction with normal materials. Okay? There's got to be some gearing between the materials before you get a frictional force that's greater than your normal force. So let's make sure it's clear that that's greater than the normal force. Okay. How do dragsters exceed the speed of, exceed the acceleration of gravity? It's not friction. Tires are hot and they're laying down rubber and they're pushing back on that rubber, but they're bonded to that rubber they're pushing on. So there's rubber sticking to the surface. Their tires are sticking to that rubber and that's pushing them forward with an acceleration greater than that of gravity. And that doesn't work when you're stopping, because when you're stopping, your tires are sliding along the surface, and that's friction. Okay. But in the case of a dragster, there's a very quick bonding of the rubber and the tire with the surface. And everything goes forward at an incredible rate. Okay. Okay, on a NASCAR track, as you know, if you've ever been down to the track, 20 miles from here, uh, the track is banked because cars can't go around that short track at the speed they go because the friction they need to supply the centripetal force, keep them on the track is not sufficient. You know, if you go around a curve too fast, you're going to spin out, or at least slide out. And usually when you slide out, you spin because of various, where's the center of mass of the car and all that stuff. So what you're doing is basically, okay, your car is coming around the track here. Here's your car. Got some tires. This is a rear view. So the track's going around this way, and we kind of slice the picture this way. So you got some angle theta here. Well, you got MG here. And you sketch your free body diagram with x-axis here and a y-axis here. So if you have a problem with a car on a banked curve, you start with this picture. And you sketch components of the weight. Well, you don't want to make that slightly. Okay, so you got this. And you've got this. So if it's you sitting on this track, you might just slide down the track. You got a good pair of rubber shoes on to keep you from going, but that's almost 45 degrees. That's not a walkable incline. Okay. I built my 45-degree roof single-handed, and I guarantee you I didn't walk on it. When I was putting up stuff, I had 2x4s across. I'd walk those 2x4s. And that was easy to do 23, 4, 5 years ago. I wouldn't get up there now. But okay, basically that's just a steep track. You wouldn't be able to walk up or down it. And some tracks are way steeper than that. This force has components X prime, Y prime axis. So this component of this force is what helps supply your centripetal force. Okay? In other words, that force is centripetal. This is toward the center of the track, if you're on a circular track, or the center of whatever circle you're temporarily on. Okay? The downward component of this force isn't particularly important, as long as you're going fast enough that you don't start sliding down the track. Okay? And if you're not going fast enough to start, if you're going too slowly to stay up on the curve, you're not going to get up on the curve. Okay? Or if somehow you come to rest on this curve, you're just going to slide down to where it's gentle. You're probably not going to tumble unless something trips you up. Okay, well, you have all those factors. The whole thing is, though, this free body diagram for the X and the Y coordinates relevant to the incline give you this force. Your centripetal force is going to be in this direction. And that's where a lot of your centrifugal force comes from. You also have a frictional force. Because of course you have a normal force here. So you got a normal force here. So you could have a frictional force is going in the wrong direction. If you're going fast enough, your frictional force is going to be down here, and it's also going to help out with the centrifugal force. You can read about it, but those are your pictures. If you're trying to slide down the incline, your frictional force will be back in this direction. In this case, you think about it, the frictional force will be in this direction, and it's going to help you stay in the curve. Okay, another situation. It'd be like this, where these 2 points are not necessarily at the same angle. And we talked about how to analyze that last time. You had a free body diagram for that 2 chapters earlier. So I expect you'll be able to draw the free body diagram for this situation and analyze it. You'd have to know the angles, one way or another. Maybe you know the angles with horizontal. But you find the tensions. And you know the mass here, you find the tensions in these 2 wires. We don't have time to go any further with that, but remind yourself of how to do a free body diagram in that case. Another important situation that we're going to look at in lab on Friday is an Atwood machine. And I kind of know where my pulleys are, but I've got to do a little digging to bring them out of storage. But I'll do that tomorrow afternoon. Okay, you got a pulley. You have a mass M1 over this side. And a mass M2 over this side. What forces are acting on these 2 masses? You got M1G here. M2G here. Now, are both of those masses falling? Not unless your rope breaks. So why aren't they falling? What is it that's holding them up? Well, if we don't have much friction here, and this mass is a good bit bigger than this one, this thing's going to descend in this direction, right? One's going to go down, one's going to go up. Well, how does that happen? Well, the answer is that you have tension forces. You have a tension here. And you have tension here. And assuming there's no friction, these 2 tensions are equal. One's pulling on one end of the rope, the other end of the rope is pulling. The rope is trying to contract because it's been stretched. And it's pulling here and pulling here with equal tensions. Now equal, give or take a little bit of friction in this pulley. Because things going this way, friction in the pulley is trying to pull you this way. So the tensions aren't necessarily going to be. And you can draw a diagram to figure out how that goes. So what you have is mass M1, you got M1G and T here, where if mass M1 is less than mass M2, tension is going to be shorter than your M1G. Okay? Shorter than your weight. The tension is going to be less than your weight. So what is the acceleration? That'll be M1G minus T over M1. And since T is less than M1G, actually, we're going to consider up to be positive. So let's do it that way. It's T minus M1G over M1. Okay, now M1G is greater than T, so you're going to have an acceleration that's negative, in other words, downward acceleration, right? You can also do the second mass. M2G being a longer vector indicating a bigger mass, and a tension being about the same length, because that's what we have. So we're going to call this A1, and we're going to call this A2. And that's going to be when I drew these, I just got out of bed the wrong way this morning. Let's go back to this. When I drew this tension, both of these tensions, I should have gone a little longer. So this one is still shorter than this one, but this one's now longer than this one. So my proper picture would have been, but I wrote it first. This one was all right, and this one, the tension is less. So it's acceleration 2. Okay, this acceleration is and we're just out of time, so I'm just going to wrap it up fast. is accelerating upward at the same rate this one is accelerating down. So that I can say that this is equal and opposite to this. And we get the equation T minus M1G over M1 is equal to the negative of T minus M2G over M2. Since we know M1 and M2 and G, we can solve for T. Solving for T, we can calculate the two accelerations. Okay? And that's what I'm trying to get to. There's a formula that comes from this, and it's kind of a neat symmetric formula that you're welcome to use because it's such a neat formula. And make sure you know how to do it, starting with the free body diagram. Okay? And I'd really prefer to see that in your solution rather than that formula. It's a nice symmetric formula. It's kind of a good feeling formula. And there's actually a good intuitive connection to that formula. Okay, well, we're out of time. Some of you need to go to work. Some of you need to do other things. We'll see you on Friday.